Okay, good morning. So let's start the application layer section of this course. And this is dedicated to the first upper layer in the protocol stack we have introduced in the previous lessons. Applications are all the various popular softwares that you know, and maybe from web browsing, email, social networking, file sharing, VoIP, and so on and so forth. And here you see some statistics about the intensity that is generated by the different applications in terms of downlink traffic. We have already introduced the concept of host, that is the computer hosting the processes of the applications that are running, and the network is used to transfer data from one host to another. And the layered architecture we have seen is very good because it has the advantage that separates or makes say updates or changes at the different layers independent one each other. So if you want to invent a new application, you don't have to modify the network. You don't have to touch network devices except the hosts. So the hosts are already there to run the software you want to deploy, while the rest of the network is completely transparent or agnostic. So applications are actually implemented with processes that are in execution in hosts that are far apart. When you have multiple processes in execution, that is, and you exchange data between processes, this is carried out by the inter-process communication tool, that is the technology that allows processes to exchange information. And this is usually implemented in the operating system of the machines. Inter-process communication is a general concept. It can be between processes resident on the same host. In this case, everything is internal to the PC and maybe via memory if the processes shares the same memory locations, and usually these are called, it's common in the so-called multi-thread programming, or maybe through the bus. No? So in that case, you involve also the rest of the PC. But this does not require, of course, the network. While if processes are resident on different hosts, then you need the network. And so we have already seen the concept of addressing process by an identifier that allows you to distinguish between processes that are in execution on the same machine, or better said, that are in execution on the same device that is connected with the network with a single network interface. Okay. So these are the way to address the process is by using the port number. So when you have to communicate between remote processes, first you need the addressing, so the identification of the process. Then you also need something that tells you what language to speak, what kind of messages can be exchanged, what is the syntax and what is the semantic. And this is basically the function of the application layer protocols. So the application layer protocols allows standardization. So it means that interfaces from the processes to the rest of the network and the transport layer are standardized, so it becomes open. And in particular, this allows to implement, for example, the client and the server by different software houses, by different, or even with different languages and so on and so forth. So the protocols at the application layer have this function of making interface between processes and the rest of the network open. And you know already that the interface, these interfaces are also called APIs. About addressing application processes, we have already presented the concept of multiplexing and demultiplexing, and in particular the transport layer, which is managed by the operating system of each computer, interfaces above with several applications that can be running on the same platform. So this means that the transport layer has several service access points towards the application layer, and so you need to identify each service access point, because when data are going towards the application layer, you have a demultiplexing. When data are going towards the network, you have multiplexing function. Okay. And so the addressing is the system of addressing is used by the port number. So when you have a process that is in execution on a certain host, there is a first identifier, that is the IP address, which identifies the host, or better, the network interface of the host. And then a second identifier, that is the port number, identifying the service access point between the transport layer and the application layer. This is basically the same concept, but with some more details. So when you have an application process that is talking with another application process, application messages are released in the server side. So, say, for example, you have the sender side, and you have the client, are released to the network through the transport layer by placing this data or handling this data to the operating system. This is very similar to taking the garbage outside your house, because you take the garbage when you need to get rid of the garbage. This is not necessarily synchronized with the garbage collecting service, so the garbages are then collected at a different time. And in a similar way, the application process writes the data on the socket, waiting for the transport layer to take the data and transfer it to the destination. And the same in on the other way, when data are delivered to the destination application, the destination process, the transport layer writes data to the socket buffer, this buffer associated to the socket interface, and when the destination process is ready to read the data, then it can read the data in an asynchronous way. So you have not independently coupled the dynamic behavior of the network with the behavior of the single processes. Applications are of different nature, so each application has different requirements in terms of the so-called quality of service. Typical parameters by which you can measure this quality of service are the data loss probability, the bandwidth, and the tolerated delay. So an application that is not tolerant to data loss requires a very strict control over error, possible errors. Applications that are not tolerant, that are strict in terms of bandwidth requires another form of protection, let's say, of service. And also, there are also applications that are sensitive in terms of delay. Typically, the real applications that are real time, so, for example, real time audio or video, like a phone call or a video conference, are very sensitive in terms of delay and also in terms of bandwidth. Video applications, not necessarily real time, are usually sensitive in terms of bandwidth, so they require minimum bandwidth, otherwise the application is not satisfactory in terms of the users. While other applications that basically implies the transfer of files or computer data usually are not tolerant in terms of data loss, but tolerant in terms of time sensitivity and also elastic in terms of bandwidth. For example, when you transfer a file, the time it takes to transfer the file usually is not very strict. There are no requirements, and this implies also that the bandwidth, or when you transfer this data, is elastic in the sense that this particular transfer takes the capacity that is available. Okay. In some moments, you can have a large capacity available, so the bandwidth will be large, but in other instance, maybe the network is more congested, the bandwidth will be small, but this does not jeopardize the application of file transfer. So according to the different application requirements, applications requires different services to the network, and in the context of internet and of the TCP/IP protocol stack, two main services have been defined. One is so-called TCP service, and the TCP service is connection oriented, so it means that there is a setup of a connection before exchange of data. It's very reliable, so there is the guarantee that you don't have data loss. Has also a flow control and congestion control. It does not guarantee bandwidth and delay, because this is not out of the capabilities of this kind of networks. But it's very good for all applications that requires transfer of files. Okay? So for example, SMTP, Telnet, HTTP, FTP, we will look at them. They all require a TCP service. On the other side, you have the UDP service. Transfer is unreliable, it's connectionless, you don't have control of on traffic or guarantees about errors, but it is fast, so it's very good for all applications that requires that are very sensitive in terms of delay. For example, interactive applications. This is also good for applications that are sensitive in terms of minimum bandwidth, like for example multimedia streaming, and this is actually not a property of specific property of UDP, but with TCP, in order to have flow control, reliability, and congestion control, there are mechanisms that tends to reduce the bandwidth of a single connection in some occasions. So if you use TCP for example, multimedia streaming, then in some cases the TCP mechanism overreacts to congestion and restrict the bandwidth too much. So this is not very good for multimedia streaming services. So this is why UDP service is better in these cases. TCP service and UDP service are then associated to two different protocols at the transport layer, as we will see later on when we will go from the application layer to the transport layer. Questions so far? The application layer is not a single protocol, actually is a collection of protocols, and the very important decision that was made in internet was that the application layer protocols were specific, had to be specific for each application. Okay? So different applications implies different protocols at the application layer. Some of those protocols are standardized or open, defined by IETF recommendations. Some others are not standardized, so they are, let's say, private or not accessible. So with standardized protocols, you have the possibility of developing software by a pool of developers, while in the other cases, with proprietary protocols, only the ones who develop that specific applications are entitled to produce software. So we will have a look only to the standardized protocols, of course. This is something that I have already introduced in the first lesson. So there are two main paradigms for the application layer. One paradigm is based on the client-server architecture, and in this case, the hosts that are in communication, so the processes that are in communication at the application layer are not symmetrical. But in one host, we have the implementation of a client process. On the other host, we have the implementation of the server process. And so usually the server process that is implemented in the server is able to manage several requests from different clients. The server has to provide replies, the clients make questions or requests. The server should be always on, because otherwise you don't know when the server when the next client will make a request. So it must be on in order to accept the request. It must be always identifiable inside the network with a unique address, so the IP address associated with the server is usually permanent. Sometimes it is implemented not as a single machine, but as a cluster of machines, because it has to respond to maybe several requests at the same time, and so it can receive multiple clients. Instead, on the client side, the host can be connected discontinuously, because it may access the network only when the user has the need to use that specific application. So you can change the address. Clients do not talk to each other directly, otherwise they're not a client anymore. And a single client may also send multiple requests to the same server. The other paradigm is based on the peer-to-peer architecture. So all the hosts in these communications that are involved in these communications are not server nor client. Actually, they play the role of the server and client in different moments, and they are discontinuously connected, can change the IP address, and this is implies that these architectures are more difficult to manage, okay, compared to the client-server architecture. But they have advantages, as we will see in the final part. So let's start with the first protocol at the application layer, that is a Hypertext Transfer Protocol, HTTP. And this is used for the web browsing service. So it was invented by Berners-Lee, as we have already seen. This protocol is used to transfer objects from the server to the client. So the client makes requests of getting objects, and the server provides the objects and sends them to the client. These objects are usually files, and they are usually also grouped in groups. Each web page that you can access on a web server is linked to several objects. Each web page is usually an HTML file itself. So it is, first of all, you find the HTML file of the web page. In the HTML file, there are links to other objects that may be, for example, pictures like JPEG, audio, video, or audio files, video files, Java applets, links to other web pages, and so on. So the HTML-based file is downloaded first when the client makes a request for a web page. First of all, the server replies with the HTML file, and then the other objects are downloaded as well. And we will see that there are different ways in order to download the other objects. In order to identify a specific object in the HTTP architecture, we use the Uniform Resource Locator. The Uniform Resource Locator is a text string, so a set of characters, where you find as a first word the name of the application protocol that is used. Usually it can be HTTP or HTTPS to the context of web browsing. But URL are not used only with HTTP, but also with other protocols. For example, you can find FTP if you're using FTP. Okay. Then there is semicolon / and then you have the identifier of the server. Here you see a name. Okay, it is called the symbolic name. This name corresponds to an IP address. Okay. We will see later on how we can pass from the names to the IP addresses. But in any case, this is an address of the server. The interface, network interface of the server, it can be expressed in a form of an IP address or a number or a symbolic name. Then you have the port number that identifies the process, as we have already said. So it is the identifier of the process on the server that you have to contact. And finally, a file name that is the requested web page. Okay? It can be simple file name or in the form of a path with then a file name. So this is the URL. The architecture is relatively simple. You have the clients that can be usually browsers implemented in several kind of platforms like PC, smartphones, and so on. and the client makes HTTP request to the server returns HTTP responses. The popular names of client implementations are Firefox, Safari, Chrome, Internet Explorer, and so on. Popular name of server implementation, Apache. HTTP is a stateless protocol. This means that the server does not keep track of past requests received from a client, the same client, or from another client. And so therefore, each time you access the server, for the server is the first time. Then we will see that there is a mechanism that allows to say make something that is makes the protocol almost stateless. All these requests and responses are messages in the format that is specified by HTTP protocol. Okay, so the HTTP protocol defines a format for messages for request and response. HTTP requires a TCP service from the transport layer, so it means that it uses TCP protocol in the transport layer. Okay, so messages of HTTP are encapsulated into segments of the TCP protocol, which are then encapsulated into IP packets and encapsulated into, for example, Ethernet frames and so on. Okay, so the protocol data units of HTTP are encapsulated, are carried inside as a payload of the protocol data units of the TCP protocol. In order to identify the server, there is always the same conventional port number, which is 80, which is associated to HTTP. So each HTTP server, each web server, has always a port number 80. And we will see later on how this is important when we will study the transport layer. On the other side, the port number of the client is assigned each time the client starts its operations, is assigned randomly. Okay, so the client does not have a specific port number for HTTP. So the HTTP server accepts TCP connections when the client wants to start using this service, and then they exchange information once the connection is set up. So since this is a connection-oriented service, you have always a setup phase. The setup phase is used to set up the TCP connection between the client and the server. After the exchange of information on the TCP connection, then the connection is closed. You have also a closing phase. And here we start dealing more with the details. There are two different modes in which you can manage the connections with HTTP. The first mode is called non-persistent connection, and this is typical, it's the only mode possible with the first version of HTTP, which is called version 1.0. It is called non-persistent, and it means that each time you have to download or receive an object from the server, a connection is set up and then closed after this object is transferred. Okay. So since, as we have said, when you access a web page is a collection of objects. In order to retrieve each of these objects, you need to set up a connection and close it. So first, the client will receive a HTML file of the web page. The client and the servers have to set up a TCP connection, transfer the HTML file, close the TCP connection, and then the client starts requesting the objects that are linked by the HTML file. Okay, is the client that looks at the HTML file object that is received and starts asking for all the objects. For each object, you have to set open a connection, transfer the object, close the connection. This process can be also carried out in parallel. So if the software implementation of the client, and of the service allows that you set up multiple processes in parallel, and you can manage them in parallel. These requests can be done in parallel. The other possibility is the persistent connection. In this case, a connection is opened when the first time that the page is accessed or requested by the client, and then the connection remains open for when all the objects are downloaded. So, for example, here you start to open the connection, you start downloading the HTML page, and then the connection remains open. You download all the objects like images and so on. Connection remains open until the connection is closed. And with these persistent connections, you have two possible modes. One is without pipeline. The other one is with pipeline. Without pipeline, it means that the client does not make a new request for another object until it receives the reply to the previous request. Okay. With pipeline, the client can start sending requests one after the other without waiting for the replies. At the condition, however, that all the replies will arrive in the same order as the requests. Okay. So first a request is done for an object, then maybe you do a second request for another object, but the second object cannot be received by the client until all the first object has been received. This is an example where you see a client that is requesting a specific page. So the client sends a request for the URL polylit.it home index, which is the web page of Politecnico. Then the server that is has a waiting process that is running on port 80 in order to wait for requests from clients. As soon as it receives the request, it starts accepting the connection, so the connection is set up. Then the client can send the request for a specific object once the connection has been set up. When the server receives the request for that specific object, it sends the document, in this case the HTML file. Then the connection is closed. In this case, we are looking at a non-persistent connection. So it means that once the client receives the HTML file, it starts analyzing the page, and then it can start asking for the objects that are linked. And for doing this, it will need new connections to be open and closed. an important parameter that we to estimate when we are looking at this kind of protocols is the total transfer time of a single file or a set of files is page. And so since the client and the process and the server are located in two different hosts, to analyze this exchange, we just need to know what is the so-called round trip time. So the time that it takes for a packet of generic signal to go from the host to the server and then come back. Okay. Yes.
There's that past slide I want to ask you about what is the difference between persistent connection and non-persistent. Like in practice, where do you have to use which one of these?
In practice, it depends. If you are using a protocol that allows you persistent connection, it usually is better to use it because we are looking at when you are looking at this exactly this evaluation. Each time you have to open a connection. This requires a round trip time, okay, just to open the connection. So before sending data, the TCP connection must be active. Okay. In order to open the TCP connection, you have to exchange messages between the source and the destination at the transport layer. And so this is, you can when you are analyzing the application layer, you're not interested in what happens inside the network, but if you know the round trip time, so the time that it takes to go from the client to the server and back, that's enough. And you know that to open a connection, you need a round trip time. Once the connection is open, the client can send the request, and then once the server receives the request, can start sending the file, the object. Okay. So the total time, okay, that you have, this is exactly the answer to the question. The total time for doing this transfer operation is calculated in this way. If you have a non-persistent connection, and you have to download a set of 10 objects, maybe the HTML file plus the 9 pictures. Then for each object, you must count a round trip time for a connection opening. Okay. Then there is another round trip time because the client has to send a request, and the server has to wait for this request and then start sending before sending the data. So this is from here to this instant here, you have another round trip time. Then you have to take into account the time that the server needs to transmit the object. Okay. Usually objects are long, so the messages that are exchanged in order to set up the connection and to ask to make the request are very short because they are just control messages. But when the server sends back the object, it contains data, so it is long. So this is what you have to take into account for a single object in the case of non-persistent. So twice round trip time plus transmission time of the object. In non-persistent connection, you have to sum these two components for each object. In the persistent case, the connection is open only once every minute. So you save one round trip time for all the objects. If you have n objects, you save n minus 1 round trip times. This is the advantage of the persistent. Obviously, the transmission time is dominant and the round trip time is negligible. They are practically the same. but in the other cases, they are not safe. You can do it only if the protocol allows you to manage persistent connection. So HTTP version 1.0 does not allow you to manage persistent connections, but HTTP version 1.1 allows you. Okay. What is the format of these messages? As I said, there are two different formats, one for the request and the other one for the price. And generally speaking, in the application layer, everything is very textual. Okay, so in order to be easily readable also by human beings. And the HTTP messages are always coded in an ASCII format, so to be human readable. And they are composed of these fields. So there is first a request line with several fields, then a set of header lines that are specifying parameters, and then the body. So the header of these messages at the application layer is composed by the request line and the header lines. Okay. Each line is separated by another line by carriage return and line field characters that are encoded in ASCII. And then the body carries the possible information. For example, get the index HTML and the line that you read above is a request, and this is the request line. Okay. The first word is the method, and the method is basically the instruction or the command that the client sends to the server. Then you have the URL, the identifier of the object. Then you specify the version of HTTP. In this case, HTTP version 1.1. Okay. Then you have all these header lines where you specify several things. Look at them also later. For example, you can specify what is the user agent, so implementation of a client, what is the language that is accepted, the rest of the host, and so on. And then there is the body. Body is not present in all the request messages. For example, in the get message, you don't have any body, any data. But in other, with other commands, you may have, and these are the most common commands or methods. There is the get that is used to retrieve an object. Header when you just want to download the informations about the document, but not the whole document. Post is used to provide input to the server for a particular object, usually, for example, an application. Put instead is used to upload documents on the server, if you're allowed to, of course. And in this, for example, in the post and the put case, you have also the body, because the transfer contains contents from the client to the server. Delete to delete, to remove a document in the server. The headers are always in the format of lines, different lines, and each line has a header name and then a header value. Of course, the value depends on the type of header. So, for example, in accept, you have a set of formats. Means, for example, if you're accepting JPEG or text formats and so on. So here you will have extension, file extension. Accept language identifiers, authorization to send the password, for example, and so on. And you can send multiple line headers in the same object, in the same request. This is instead the format of the reply, which is quite similar. Again, you have the first line, which is in this case is called the status line, and then the set of header lines, usually in reply of the header lines that have been sent in the request, and then the body with the content. This is an example when this is the reply to a get. Okay. And the first line tells, again, the version of HTTP, status code, and a phrase that explains the status code, so associated with the status code. And then you have the header field, and then the body. In the replies, you don't have the name of the method as in the request, but a number that is a code that identifies the type of replies. So, and this status line coding works in this way. You have groups of different codes, and the group is identified by the first decimal digit of the number. So then you have other two digits that identifies a specific code in a group of code. Of course, you don't have to learn all these things, but just to remember the groups. The first is returns information. For example, reply to a head request is this type. 2 identifies the success. 3, so that the request was correct and the object that has been requested is sent to the reply. 3 is a redirection. The request is correct and redirected to another server. And then 4 and 5 are served for as error identifiers. 4 is on a client-side error, for example, if the server receives a request that is not formatted properly. 5, server-side error, for example, if the server goes down while sending a reply. And these status lines are, however, also explained in terms that is human readable. So this is a full example of a request and a reply. Request for a specific HTML file, and the reply is okay, so the file has been found. There is a possibility of using the so-called conditional get, and this is done by sending a request with the header if modified since, followed by a date. Okay. The date is the time. The time is specified in terms of date, so day, and also specific hour in the day if needed. So what is the conditional get? Conditional get is a request that says to the server, do not send me the object if it already exists at the client in the browser cache. And the date of the object stored in the local cache is inserted in this header if modified since the date. This is because all the clients have a cache. So when usually the cache is used to store objects that are taken from the server, or your browser has a cache, perfect. No? So when an object is already in the cache, it's better to get it from the cache instead of waiting it from the server. But the object has been cached in a specific time, okay, in a specific moment in time. After this moment, the server may have modified the object and have changed the file. So it's reasonable to accept to use the cached version only if the original version has not been modified after the caching date. So this is how it works. So in the message, in the request message, there is an if modified since. So if the object is not modified after the date, then the response is not modified. Okay. So group number 3, not modified. If instead the object has been modified after the date specified, automatically the server sends the object again, because this is a new version that has to be replaced in the cache. Okay. So this is basically the behavior of this conditional get, which uses this if modified since header, which is one of the most important headers that you have to see. Then there is another use of headers, which is called the cookie. I'm sure that you know already this name because it's very popular. And this is a method or a mechanism to overcome the stateless nature of HTTP. So it is obviously an advantage to have this protocol stateless, because otherwise in the server you should have a very huge database of all the requests from the clients. But sometimes it's desirable that the client that returns to the same server is immediately identified. Okay. And this is done with the cookies. So the ingredients of this system are the following. First, you have a cookie header in the HTTP replies. Then, by the cookie header, the server is say, sending content to the client, but at the same time, it is sending also an identifier of the client. So the client can decide to use this identifier and put it in the cookie header of the next request. Okay. The server maintains a list of cookies stored in the server. Sorry, a database stored in the server, and the client also maintains a list of cookies. So if the client wants to use the cookie for the next request, then it sends this code to the server. If the server finds the cookie in its database, the server can identify immediately the client. Okay. So, for example, does not ask again the same questions to the client, or provides the cart. When you are doing e-commerce, you have the cart where you put goods. So the server, if you access the server in a session and you put some goods you want to buy in the cart, you get out and you get in a new session. Usually the server remembers what you have in the cart, and this is done by using the cookies. So this is an example. This is e-commerce. So when you visit the site for the first time, then the site generates the ID, that is the cookie code, and then it opens a new entry in the local cookie database with the data of the client that has visited the server for the first time. Then this is the first request, and then it's the generation of ID and generation of a new entry in the backend database of the server. Then the server sends the response, and it sends it along with the ID that has been created, that is inserted in the set cookie header. Next time the client wants to access the same server, it may decide, this is upon user decision, to use the cookie. So the cookie is the code that has been received is put in the request, and then since there is a corresponding entry in the database, the server is able to identify that specific client. This is, of course, in the same session, but the cookie can be used also in another moment in time, for example, after a week. If you access the client with the cookie, you are the server with the cookie, you are again identified. Okay. Another interesting things to know about HTTP is network caching. So not only we have the local caches in the clients that can cache the content received from the server, but there is also the possibility to use HTTP proxies. HTTP proxies are network elements, so part of the network equipment, and an HTTP proxy is able to receive requests from the clients and then to receive the answer from replies from the servers and to cache the replies. So all the clients, if there is an HTTP proxy defined, all the clients send the request to the proxy, and if the request object is not in the cache, then the proxy will send the request or forward the request to the original server, will get the content of from the server, the response from the server, so it will store the object in the proxy cache, and it will use the object to send the response to the original client. Okay. So in this case, and then the client has the object. If another request comes from an object that is already in the cache, in this case, the proxy does not forward anything to the original server. It just directly responds to the client. This, of course, has a lot of advantages because in this way you can offload the servers from a lot of jobs and also offload the network that is behind the proxy. The proxy is an application gateway, so it's a network element which, however, implement all protocol layers from the physical to the application. And it plays the role of both the client and server. So with the original client, it plays the role of the server, and with the server, it plays the role of the client. We have talked about HTTP version 1.0 and HTTP version 1.1. There is a new version of HTTP which is has been released some years ago, but slowly replacing the use of the older versions. This new version has many advantages. You can reduce the latency of downloading large web pages and solve other problems of HTTP. Today, the most common web pages contains hundreds of objects. So it's very important to improve the possibility of downloading these objects quickly. And already going from the non-persistent to the persistent mode, as we have seen, is an advantage. But HTTP version 1.1 using persistent connections still is not the best, because there is the head of the line problem that I will show you in a few slides. HTTP version 2 has introduced many differences. For example, messages are not transferred in textual format anymore, but they are transferred in binary format. They are called frames, and can manage multiple streams over a single TCP connection. Each stream has a stream identifier. And then also there are some functions that allow to compress the header and additional functions like server push, flow control, and so on. And there is, for example, this page from Akamai, which can be downloaded, accessed in order to compare the two protocols. I hope it will work here. So this is the same object that is downloaded in HTTP version 1.1 and in HTTP version 2. Actually, here the network is very slow, so you don't see it visually very much, but the estimated load time in the two cases is different. So in the first case is 9 seconds, in the second case is 5 seconds, which is quite small. Latency here is an estimation of the round trip time. Okay. So going back, if you try it at home, it works better. So just to have a fast look at the main features of HTML version 2. Header compression is very important, especially when you send large headers, like for example using a lot of cookies. So this makes the header very large, but information that is sent in the header, for example, of HTTP version 1.1 is redundant because a lot of parameters are repeated identical from one HTTP request to another. So HTTP version 2 introduced techniques in order to compress these headers. For example, most common symbols or sequences of words, of letters, are encoded into binary strings. Okay, so, for example, if A, that is in the previous versions, is encoded in ASCII, so it takes 7 bits. If it is a very common string, then it can be encoded, for example, in 3 bits, or C in 1 bit, and so on. So the word accept, which is 6 bytes when encoded in ASCII, can be sent in just 2 bytes. This is applied also to header lines. So header lines that are very common are associated to an index, and only the index is sent. And then in subsequent requests, you only send the differences and not the whole header. This is an example. Below you find the HTTP1 implementation. this is one request, this is the next request. So in HTTP 1, you don't have any kind of compression. In HTTP version 2, you have compressions. For example, the line that is method get, since it is very common, it's encoded in the number 2. So you send number 2 instead of the whole line. And the same for the second line. 38 that is corresponds to host, and then you have the URL of the host. The URL of the host is repeated in several messages, so also that one can be encoded into a number. So you see that in the second request, you don't send the URL here, but you send us the number 60, and so on, okay, and so forth. The other new advantage that is introduced is management of transmission of messages into frames. I don't go into the details of these frames, but this is very important to understand how multiplexing takes, how multiplexing occurs. So this is a session in HTTP version 1.0. You don't have persistent connection. So you have black arrows are for the opening of the TCP connection. So you have 3 objects to send, to receive. The one is very large, the green one, and then you have 2 that are smaller. For each object, you have to open the connection, send the request, and wait for the object. With HTTP 1.1, you can use the persistent connection. This is the version without pipelining. So there is the opening of the connection that is only occurs once, and then you can download the 3 objects. HTTP version 1.1 with pipeline improves again, because you can send requests and then you receive the replies without waiting for a reply. But you can see here that the first object is very large, so the other 2 objects have to wait until the first object is totally transferred. Okay. So it means that for the other 2 objects, the client experiences a very large waiting time. What happens with HTTP version 2? Since you have this stream control, so the transmission with streams, you can shuffle the objects. So, for instance, the green object, since it is very large, is set into chunks. You see the first chunk of the green object, then the red object, another chunk of the green object, then the blue object. So in this way, the small objects don't have to wait for a long time. And there is no head of the line blocking as in HTTP version 1.1. Finally, this is another interesting feature. It's the push. It's called server push. In the previous versions, as we have seen, the client receives the main page, has to analyze the page, and then the client has always to explicitly request the other objects, okay? Sending each one request for each object. In HTTP/2, the server proposes the client already the objects. Okay, so when the client first accesses the page, the server proposes the client to send all the linked objects without waiting for explicit requests. Okay. So if the client is in the mode in which it can accept this server push function, it receives all the page, complete page immediately. Finally, just a few words on HTTPS, which is HTTP safe. So what happens if we use HTTP for an e-commerce application, for example, to buy something from Amazon? We can have several kind of attacks. So an attacker can catch the HTTP messages that contains the data of the credit card that I'm using to pay. This is absence of so-called confidentiality. An attacker may modify the messages that request the purchase, for example, making me buy 10 objects instead of one. It's called data integrity, absence of integrity. And an attacker could masquerade as Amazon and steal information or defy the band, and because there is no authentication. So when the client send the request to the server, the client cannot be sure that the server is exactly the one that we want to target. So in HTTPS, that is the safe version of HTTP, suitable for secure transactions, these issues have been addressed. Okay, and the method to address the issues, the tip if you want, is not to modify HTTP itself, but to modify TCP. So we use TCP connections that ensure confidentiality, integrity, and authentication. Okay. In order to do this, there has been another sublayer that has been produced on the top of TCP, which is called TLS, Transport Layer Security. Once it was called SSL, so Secure Socket Layer. So usually you find both the names. This protocol allows to make open connections that are safe. Okay, we don't go into the details, but if you want, you can read these slides that are in the set. Obviously, this topic is outside this course, but if you want, there are several courses that are offered, for example, network security and cryptography, computer security, and so on, okay, when you can deal with these things. So now I don't know if we have much time. Because, okay, maybe it's better if we look at it in the next lesson, but the idea was to show you something that some practical examples that you can also do with the virtual machine that I have suggested you to download. I don't know if you have it here. So the virtual machine is actually taken from the 10 credit version of this course, okay? And it contains already tools that can be used to make experiments, especially in the application layer. So you can download this machine and try to do what we are doing here, what we are showing during the lesson. So maybe next time, because now it's really late, Sebastian will show you some experiments you can do, for example, with HTTP. There is a web server configured in the virtual machine that can be accessed by a client. Everything is with the CLI, so command line interface, but it's nice. And so he will show you how to contact a server and download the web page, and then how to manage this connection. Okay, so we do it next time. Maybe if you take your own PC, you're able to do it with us. There are some experiments that we will show in the class. Some others that are left for homework, so we don't have time to go into these days. You can find videos that are showing these experiments live. Unfortunately, they are still in Italian because they come from the other course. So with time, we will try to translate them, to make them again. Okay. So next time we will start to look into another protocol that is email. Since I have few minutes, I can start talking about it. Just few slides. This is a protocol that again belongs to the application layer. It's based on the client server, the client server paradigm, and relies on TCP. Okay, so it requires a TCP service to be set up, so connections to be opened from the service to the client using TCP protocol. And actually, email uses not a single protocol in the application layer, but a set of protocols. SMTP is the main protocol that is used to exchange messages between the mail centers. And then you have other protocols, for example, POP3 and IMA, that are used to log into a mail server and locally download or look into at your own emails. So we will see that the protocols, the main components of this system are the user agents, where you have the implementation of common clients, like, for example, once there was a Eudora, Outlook, Thunderbird, and so on and so forth. And then you have the mail servers. This is a tricky name because they are called mail servers, but as we will see later on, they play the role of both client and server. Depends on the cases. In any case, they are called servers because they are the hosts that are hosting the emails. So the messages remains in the servers when they are delivered. They are sent from a user to a certain destination. They remain in the destination mail server. And then we have the protocols. SMTP is the protocol that is used to talk between mail servers. And it is also used to send the mail, outgoing mail, to the first mail server. So the user agent, your Outlook, when you compose a new mail, it will transfer it to your mail server. And for this first hop, SMTP is used. The other protocols are instead used to manage the mailbox that you have in the server by the user agent. They are called the POP3 or IMA. Each mail server has a pool of accredited users, the users that have account on a specific mail server. So, for example, if you are in mail.polyme.it, it means that you are a user with an account on the Polyme mail server. And each mail server contains two main parts. One is the outgoing message queue, and the other one is the set of mailbox, the user mailbox. The outgoing message queue is used for outgoing messages, so all the messages that users have to send, the users that are logged into this mail server, they are queued in this queue and then sent to the destination. Instead, user mailbox are used to contain messages that arrive from the senders. And outgoing mails, email queue is shared by all the users of the mail server, while each user has its own mailbox in the mail server where he has the credentials. So a mail server receives the outgoing mails from the user client, and all the accredited users can ask to send outgoing messages. And then the mail server also receives the mails that are destined to users that are accredited on that mail server. Okay. So this mail server can receive the mails on the other mail servers, and it accepts the mails only if the destination, the final destination, is accredited on the mail server and it has its own mailbox. So when the message arrives, it's stored in the mailbox. So the mail server speaks with protocol SMTP to the other mail servers and with the user agent when receives outgoing mails. The mail server speaks with POP3 or IMAP with the user clients in the Node when the user client has to manage his own mailbox, his own mailbox and his own mails. Okay, now we can stop here. So next week, unfortunately, we lost one lesson this week. Next week we will start. So I will tell you maybe the final things about SMTP, and then Sebastian will do all the hands-on tests.